Hi, welcome back. So in this module video, we're gonna cover some regularization techniques, strategies for deep learning. So we're gonna give you a whole host of weight decay, augmentation, early stopping, drop or drop out, and many more regularization strategy. So here we go. Well, the best way to explain overfitting is this image. I really like it because think about it all. If you make it mattresses and the bed, and all you see people sleeping in this position, you're gonna be overfitting to what you have at training data. So and at the result, the mattress that you build or created, or the model that you build, is not gonna be useful for the regular population. So we gotta figure out a way to overcome overfittings here by regularizations. So first, we'd like to review some basic concept. The ability to perform well on unobserved inputs is called generalization, and the generalization error referred to the performance of the algorithm on unobserved input data. Now, underfitting is when the model is not able to obtain sufficient training errors. So if you think about this image really hit home about all of the training error and generalization errors. So if you not have low enough training errors, your model is underfitting. Now the opposite, you would have overfitting, and when your training error is low, but your generalization errors is high or start taking off here, and you have a gap between the two. That means your algorithm is overfit. And we have a discussion on Piazza on bias and variant trade-off. So hopefully it'll give you some insight from there. Now, the model capacity is important here because there is the variety of function you can fit into your model, a variety of different network architectures you can do in the neural net, and the model with low capacity may be underfitting or having some difficulty fitting to the training set, while the model with high capacity would tend to overfit or memorizing all the training instances, so will not serve well in the test set. And if you understand, the neural network with very high capacity in this model can easily overfit the training data set if we're not careful. So one way to control the model capacity is choosing it from the hypothesis space. In the neural network term, is mean that you design the layer and design the network that make sure it is optimal for the learning algorithms to achieve to the solution. So if you have a case where your model is too low capacity, you might have some underfitting. In this case, you only have a small, low degree polynomial here with degree of 1. Now, when you increase the hypothesis space or you make the model with higher capacity, you might have appropriate capacity to approximate the training data. However, if you have way too high of the hypothesis space, in this case up to degree 9, your model will fit the training data very well in this case, but it's overfit, so it won't be able to generalize well on unobserved data. All right, so where is regularization comes in? Regularization comes in when you want to modify your learning algorithm to reduce the generalization error, but not the training errors. Or if it affects the training error, it'll be very minimum. So for example, in the linear regression, we can modify the loss function to prefer a weight to have a smaller L2 norm, and we can use that at the regularizer. So you can see here we added an extra terms into the loss function beside the MSE, so that it would make sure it's also minimize this L2 norm of the weight. And then at the result, with higher number of this parameter lambda, you want to make sure the weight stay really small and your model becomes somewhat simple. If you're losing up the lambda a bit, your model become, in this case, almost quadratic. And if you make lambda go to 0, which means you ignore these terms, this way, for this high capacity model, gonna be surely to overfit. So determine the value of lambda important, as we see in the next example as well. So we will survey several regularization strategies to regularize the neural networks. And here are the 7 prominent ways to regulate the neural networks. And we're going to go over each of them in this series of video for these modules. So let's start with parameter norms. And you learn about parameter norm before in other machine learning class perhaps. Many regularizations limit the model capacity by adding the parameter norm to the objective or loss function. Right? So you're going to see this a lot. You have beside the loss function, maybe in the MSE, you can also add an extra terms called the norm penalty. Right? So represented by the function big omega here and with the hyperparameter lambda. Right? So these are the 2 terms that you need to know. Parameter lambda are going to control the contribution between the data loss and the norm penalty. And larger value of lambda corresponding to more regularizations. Make sure that the penalties are larger, right? And if you set lambda to 0, it means you don't want to allow any regularization. So this term, if lambda is 0, this term go away. So it's just back to unregulate a model. So, and the norm penalty function here, penalty only the weight in the linear affine transformation of the neural net, not the activation function. And so different choice of the function big omega can resolve into different solution being preferred. So first we're going to cover L2 parameter regularizations. It's also known as ridge regression. And the L2 norm penalty, commonly known also as the weight decay. So you might heard of these terms. Now you know what it means. And the weight decay basically just add a L2 norm to the weight W here, right? The lambda now have over 2 for the convenience of doing gradients later on, as you see on the next one. So if this loss function here, I do a gradient with respect to the parameters, it would be the gradient of the loss, data loss, what we've seen earlier. And now it's also gradient of this term. And if you do some calculus here, you bring down the square, and that cancel out with the 2, you end up with just lambda times W. And this is kind of particularly nice because it scales linearly with the weight. So when you're taking single gradient steps, what you see here is that you want to take making modification to your parameter with some learning rate with respect to the gradient with function J here. And this function J can be break down into 2 terms, the loss, data loss term and the regularization terms, right? And as you multiply this out, by the way, alpha is learning rate, multiply this out and group with W, now we can have 1 minus alpha lambda times W, and then minus this gradient term, right? So really interesting observation here is that you know alpha and lambda is both positive, so its product is positive, and 1 minus some positive will be less than 1. And that gonna time W. So what does that mean? What it means is you have W and time something that are less than 1. More, what happened is you're gonna try to shrink the weight vector before any gradient update. So what does that mean? It means that you're trying to decay your weight every update step to make your weight smaller. And that's why this is also known as the weight decay. And so the association with this is you trying to shrunk the parameter at every step. So with the movie Honey, I Shrunk the Kids. My favorite one growing up. Okay, so what is the geometry interpretation of this method, right? So imagine you have a simple coordinate of the only 2 parameter, W1 and W2, and the norm L2 regularization can be represented here at a concentric circles, right? Why is it circle? Because W1 square plus W2 square form a circle in the Cartesian coordinate. So you have multiple circles depending on the value of W1 and W2. You would have these circles. Now, you also have your data loss, which is a quadratic function. So I draw it here, but you can imagine it depends on these 2 parameter, but the loss value, think about it's like the quadratic is like a bowl go into the screen. So the deeper is lower loss. So that's what this means here. And the minimum point would be on right at the bottom of the bowl at this point. So the setting of W, vector W, to minimize the data loss. Okay, you also have another setting of W to minimize the norm penalty. How do you minimize the norm penalty? When both parameter is 0, then your norm penalty is 0, right? Of course, it's unrealistic to have that, but that's where it's right here with minimize norm penalty. Now, of course, we're not gonna, the model not gonna use for when we set the circle too small, right? Too far away from the actual data loss, right? So we're gonna grow this circle to have losing larger value of W, right? I mean, you're going to do sort of an optimization process here until this region intersect the data loss. And typically the intersect section is here, and one of the is going to be close to one of the, closer to the origin. So you know the both of the parameter is shrinking here compared to the original data loss optimized position. And what happened is might close to one of the exits, so one of the value can be very close to 0. Just depend on the geometry of your loss function. Typically, it's quadratic, and this circle, right? So if it close to the vertical exit here, then W1 going to be very close to 0. And again, if you lose up the circle too large, it may be end up with something similar to the data loss. With at that point, your regularization term is too loose, and it's not going to be help regulate very well. So hopefully this picture in mind going to help you see how the regularizations can help the learning method to find a more applicable weight that more have a better generalization, right? So this part, optimal for both terms, certainly would be better than just the data loss because it also have some constraint on the parameter, so it won't overfit to this data alone. Right? Okay, very good. The second type of parameter norm regularization is called L1 norm, and L1 norm is also known as lasso, least absolute shrinkage and selection operator. L1 norm, if you're looking at the distance sen, is also the same at the Manhattan distance city block. So the only difference is instead of L2 norm, we have a L1 norms here. And when you take in the gradient of this loss function, you end up with two terms here. The L1 norm going to be just the sine of W, sine function of W. And so it's slightly different because this to the gradient is no longer scaled nearly to the weight W. Instead, now it's a constant factor with a sine equal to the sine function of W. And unfortunately, there is no clean algebraic solution to approximate J that we have seen, just seen in the L2 regularization. So I will not show the algebraic deviation here. But keep in mind that this L norm make the parameter to become sparse or contain a lot of 0, and at the result it causes a subset of the weight in the network become 0, and so when you have 0 weight, your neuron become dead, so basically the signal is discarded. Also some geometry interpretation of L1 norm. Again, we have two exits with W1, W2. And with L, this is the data loss that we see earlier with the minimum value of W's there. Now, the diamond region is going to represent L1 norm. Why is that? Because if you take in absolute value and you add these two value of W1 and W2, it forms actually a diamond boundary in 2Ds here. So you have a diamond region. If it's too small, it's not as useful, right? And if you grow it large enough, it will intersect with the data loss quadratic regions. And what's interesting is typically because it grows into this pointy top, it's gonna touch the data loss function at one of the exits. So what does that mean in terms of being sparse, right? So what happened is if you touch right on the edge of the diamonds here on top, what happened is at this point, weight W actually 0. As you can see, W1 here is 0, right? So it zero out one of the parameters. And that kind of explains why the L1 regularization will make some of the parameter go to 0, and it make your weight vector become sparse. Again, if we grow this region too large or too loose, it no longer have meaningful and become equal, just approximate similar to the data loss. So, and you can control this with the hyperparameter lambda. Okay, next question is, can you combine multiple regularizations? The answer is yes. In this example, I'm going to combine L1 and L2 regularization, and the way I can do it is I just adding multiple terms into my loss function beside the data loss and include a mixed ratio R, right? So beside the lambda, now I have a hyperparameter R to determine the contribution between the lasso and the ridge regularization. Okay, so you can do that the way you combine multiple different regularization. So some of the tips on parameter norm is you can always start with ridge regression, always a good start to start with L2 norm. If you suspect that many of your useful may not be useful, then you can use lasso because it will cancel those signals come from those features, or you learn a way to minimize these features for you. But in practice, I noticed, I observed that most of the time L2 norm we're doing just fine. And if you just kind of worry that lasso may behave erratically, especially when you have lots of feature and not a lot of training data, then you can use a combination elastic net, what they call here. I mean, you combine the features. So again, the geometry interpolation, you've seen this too before. When you combine them, then it looked like a pillows here geometry, and it would hit touch the data point at this right very points. Okay. And this is actually both L1 and L2 norm is part of the parameter norms family models. And depending on the norm you have, the Q here, you may end up with different shape for your parameter norm penalty. Right? So you can see here different norm. Now, the next regularization trick I'm going to show you is about dataset augmentations, and this is kind of cool. Is that you want to make model generalize better? What is the way to do it? To add more training data, to train it on more training data. And well, if you have lots of training data, it's fine to keep adding them. But what if you don't have the data available? What can you do then? Well, you're gonna create additional data on this term, fake data, and augment them into the data sets. Now, how do you create fake data, right? This especially better or especially good in the object recognition when you train your training data at images, because you can make some image transformation, image processing on your training data, things like translating, rotating, cropping, brightness corrections, that typically give data a better or improve generalization. So an example here, I have a picture of a mushroom. Now, how do I create these fake data to add to my training data? Well, I can rotate the mushroom. I can rotate the image. I can crop in different position of the mushroom in the image. I can reduce the brightness of the image. I can, again, crop closer. I can uncrop it to make it larger, smaller. And rotate, I can rotate and do high exposure on this image. So I can create lots of different data. And that typically help the classifier and object recognition task to perform better. Now, notice that you can do this well on images, but sometimes you have things like the number 6 and 9 where some transformation would not be appropriate, right? Because if you rotate 6 180 degrees, you end up with a 9. Now you have a mixture between the two classes that are too confusing for the classifier. So it's not applicable into many different tasks that you have. So you have to keep that in mind. And then another example with the B and the D, if you rotate them or mirror them, you may be confusing your training data. So other way you can do it, you can inject random noise into the input at a form of data augmentation. So you have input data, you inject form of noise in it, you have new training data in the way. Now, beside the input, you can actually inject in noise into the output label. And I'm always nervous when we're talking about changing the output label, right? Because that's supposed to be the gold standard, right? Well, it is certainly harmful to trying to maximize the likelihood log p of y given x if y's are not accurate, right? If you're making noise, you're messing with the label. Well, one way you can do this is instead of directly changing the value, you give it a probability that y is correct with some probability 1 minus epsilon, where epsilon is a small value. So you kind of change the label into a soft label with some probability. And certainly, if you have a label of 1, you may make it into a high probability of being correct. Right? So you can, this protocol labels smoothing to regularize a model with softmax with multiple output by replacing 1 and 0 with maybe soft value here with so instead of 0 is epsilon over k minus 1, and instead of 1 is 1 minus epsilon. So this technique trying to prevent the pursuit of hard probabilities without discouraging correct classification, and research shown that it is prominently used in modern neural network. So I just showed you 2 regularization techniques. In the next video, we're going to continue with other regularization techniques that are very useful for your neural net. All right, until then, take care.